Hello, my esteemed viewers. Welcome once more to my physics lecture series. Today's lecture series is going to feature vector multiplication. Vector multiplication. Now, vector multiplication can be done in two ways, two major ways. One is multiplying a scalar by vector, multiplying a vector by a scalar, and the other is multiplying vectors together. So assuming I have a scalar, let's say I have the scalar x and I have a vector a. I can multiply this vector by the scalar to give a new vector, let's say b, which is x times a. So assuming I have the vector a is equal to 2i plus 5j plus 2k. This is a vector. If I am asked to evaluate 2a, say evaluate 2a. 2 is a scalar, so it implies I'm going to use 2 to multiply the vector a. So the vector 2a can be evaluated in this form. This is 2, then you open the bracket to write the vector 2i plus 5j plus 2k. This gives us a new vector. 2 multiplied by 2 will give you 4i. 2 multiplied by 5 is 10, while 2 multiplied by 2 is 4. So we have a new vector which we have obtained by multiplication with a scalar. This is quite simple, easy. We can also multiply two vectors together. If I have the vector a and b, for example, let's say we have two vectors a and b. A and b. We can multiply using what we call the cross product or the vector product. So if we are to use the cross product or vector product, we can say that A, it is read A cross B is equal to the magnitude of the vector A multiplied by the magnitude of the vector C sine theta. This and this are both magnitudes of the vectors A and B. Theta in this equation is the angle between both vectors. So we say theta is the angle between vectors A and B. However, it is imperative to state that the angle that is used in this case has to be the smaller angle between both vectors. Now, there is a condition attached to vector multiplication. If the cross product between two vectors gives us 0, it implies that both vectors are parallel to each other. So vector product yielding 0 implies both vectors are parallel. So that is the condition for using cross product on two vectors. If the cross product or the vector product between two vectors gives you 0, then it implies that both vectors are parallel to each other. In this case, theta is equal to 180 degrees. So we can boldly say that A and B are said to be parallel if a vector product is equal to 0. This is very important when working with vectors. Then assuming we have two vectors expressed in Cartesian coordinate, we want to express them in Cartesian coordinate system and see how we can come about their vector product. So this is for vector A equal to AXI plus AYJ plus AZK. We have another vector B is equal to BXI plus BYJ plus BZK. Now we can find the cross product between two vectors. In this form, we say A cross B is equal to, open the bracket and write the expression for the vector A, AXI plus AYJ plus AZK cross BXI plus BYJ plus BZK. Now, you have to use every term in this first bracket to multiply every term in the second bracket. When you do that, you're going to obtain A cross B will be equal to, we use this A to multiply this B. So we have AX, BX. Remember, we have unit vectors I and I attached, so we open the bracket for that, say I cross I, close the bracket, then plus you use A to multiply every term within this bracket. You do same for the other one. So we have AX BY, meaning AX multiplied by BY, AX BY. Their unit vectors are respectively I and J, so we say I cross J plus AX BZ. The unit vectors are respectively I and K, so we say I cross K, I cross K. We move on to the next one, plus AY BX into J cross I. You put it exactly how it appears. Since this is multiplying every time here, this unit vector appears first before the unit vector here. So we say AY BX J cross I. So we say J cross I plus AY BY J cross J plus AY BZ J cross K plus AZ BX K cross I plus AY AZ BY cross, it will now be K cross J plus AZ BZ K cross K. So we have used every term here to multiply every term here. Let's now proceed to see which ones we are to eliminate and which ones we are to leave, and know how to get the final product for the final expression for the cross product of two or more vectors. For us to proceed, let us draw a 3 Cartesian coordinate system. Let's say this is we call this one the Z axis, we call this the Y axis, and we call this the X axis. The unit vector for the X axis is I, that of the Y is J, and that of Z is K. Now we know that this direction is anti-clockwise, and this direction is clockwise. So we are going to use a convention. If I use the anti-clockwise direction, say I times J will give me K. So I will say that using the anti-clockwise direction, or just say for cross products, or just say in the anti-clockwise direction, I cross J will give us K. I cross J will give us K. So we say I cross J is equal to K. J cross K. J cross K will give us I. So we say J cross K will give us I. Then K cross I will give us J. So we say K cross I will give us J. Now let's move in the opposite direction. If we move in the opposite direction, it means we are now saying J cross I. So we say J cross I will give us a negative value. J cross I will give us minus K, since we are now moving opposite now. So J cross I will give us minus K. Then I cross K. I cross K will give us minus J. Y K cross J. K cross J will give us minus I. So if we do it that way, we'll now substitute all these expressions we have obtained into this equation. So substitute everything here into this equation. If we do that, we have that our A cross B, we can now say that A cross B is equal to AX BX, and also, mind you, there's also a step before this. Now I cross I is equal to J cross J, and is equal to K cross K, and that is 0. So for vector product I cross I is equal to J cross J is equal to K cross K, which is equal to 0. So anywhere we have I cross I, we equate it to 0. Anywhere we have J cross J, we equate it to 0. Anywhere we have K cross K, we equate it to 0. So we say A cross B will now be equal to AX BX. What you have there is I cross I, so into 0 plus AX BY. I cross J will give us K, so we say K plus AX BZ, which is this. I cross K will give us J. Sorry, I cross K, yeah, will give us minus J, so we include minus J here. Then we move on to say, this is Z, please. AY BX, J cross I gives us minus K, so we say minus K, plus AYBY into J cross J is 0, so this wipes away, this wipes away, this wipes away. We have plus AYBZ into J cross K is I, so we say I plus and let's move up. Okay, can manage here. Say plus AZBX into K cross I. This is where we are. K cross I, we look for it here, is J. We replace it with J plus AZBY. K cross J, replace it with minus I. Minus I plus AZBZ. K cross K is 0. So this is off, this is off, this is off. So we can then proceed to say that our A cross B will be equal to AX BY K plus AX BZ minus J plus AYBX minus K plus AYBZ I plus AZBX J plus AZBY minus I. So we bring all the unit vectors to one bracket. We have I, AYBZI, AZBY minus I. So we can then say AYBZ minus, since we have a negative sign here, AZBY. Close the bracket, say I, plus, we go to J. We have J here, AZBX minus AXBZ. ax bz bracket j, plus we go that of k, have a positive k which is ax by, so we say ax by, then we have a negative k minus ay bx. Okay, so this is the formula to apply if you want to calculate the cross product between two vectors. We just derived that formula, but however it's actually a little bit cumbersome, and we can also use the matrix notation to find the cross product between two vectors. So if we have these two vectors a and b, we can express them in matrix form as follows. We say ax, ay, az, bx, by, bz. We will now find the determinant of this matrix. The determinant of this matrix gives us the exact expression for the cross product between two vectors. You see how easy it is to use the matrix notation. So the determinant is obtained as follows: a cross b is equal to, we first of all take this I as a multiplier. Once you are using I as a multiplier, you ignore the column that I is appearing on top, and you multiply the other two columns diagonally. Diagonally means this, so ay bz, then you subtract this from it, minus az by. Close the brackets. In this matrix notation, there is a sign for each column. There's a sign for each column, and that sign is this. For the first column, you have positive, second is negative, third is positive. So we make use of this negative sign here now. Say minus j into, once you are working with j as a multiplier, you exclude the column containing j and multiply diagonally. So you now say ax bz, so ax bz minus az bx, az bx plus k. Now we are going to repeat what we've been doing. If we are using k as a multiplier, we'll have to ignore the column of k and multiply diagonally with this. So we say a x by minus ay bx. If you compare these two equations, you see that they are exactly the same. This is for I, which is this. Now, if you take note, there's a negative sign here and there's a positive sign here. If you check inside, we also have a negative sign, but check and see that they are interchanged. This negative and this positive will give you a negative sign, which is this. While this positive sign and this positive sign, this negative sign, and this negative sign will give you a positive sign, which is what you can see represented here. So you look at it carefully, you discover that both equations are exactly the same. So it is more advisable to use the determinant notation to find the cross product of two vectors. So let's look at an example on cross product. Just want to look at an example of cross product and possibly finding the angle between two vectors. So I'm going to wipe this off, then take a look at some examples. So assuming I have two vectors A and B, let's say one vector A is expressed as 3i minus j plus 3k. I have another vector B is equal to minus I plus 2j minus k. If I want to find the cross product between them, the cross product between A and B, I'll just simply use the matrix notation to make it easier. So I say A cross B is our solution. So A cross B will be equal to, we draw a matrix I, J, K. Remember to include the signs. So this is AX is 3. So we write 3 there. AY, the coefficient of J is minus 1. So we say minus 1. That of K is 3. Go to that of B. You have minus I. So the coefficient there is minus 1. Say minus 1, 2, and minus 1. This is likened to be this IJK, AX, AY, AZ, BX, BY, BZ, plus, minus, plus. So to get the value, we just simply find the determinant of the matrix. So this will be equal to I. Remember what we did previously? This is I. So we block this column and work with J and K. So we say I into, we multiply diagonally, minus 1 times minus 1 minus 3 times 2. Close this bracket, say minus J into, if you are working with J as a multiplier, you have to ignore the column of J, and so you block this column out and multiply I and K columns diagonally. So it becomes 3 times minus 1. So say 3 times minus 1 minus 3 times minus 1. Close this bracket, plus K into, if you are working with K as the multiplier, then you have to ignore the column of K and work with I and J. So we block this off and multiply diagonally. So we have 3 times 2 minus 1 times minus 1. That is both of them. So this gives us I into, minus 1 times minus 1 is 1, minus 6. Then minus J into 3 times minus 1 is minus 3. Minus 3 times minus 1. We got 3 times this, so we say minus into 3 times minus 1 is minus 3. Plus K into 3 times 2 is 6. Minus 1 times minus 1 is 1. Then we evaluate further. 1 minus 6 is minus 5. Minus J into minus 3 plus 3 is 0. Plus 6 minus 1 is 5, so 5k. So our answer is that A cross B is equal to minus 5i plus 5k. See how simple it is. We can also find the angle between A and B. Recall that the angle, the cross product between A and B is expressed as this, sine theta. So the angle will be sine theta is equal to A cross B, that is the magnitude of this, all over magnitude of A times the magnitude of B. So we have to go further to find the magnitude of both A and B, and also the magnitude of the cross product between A and B. So let's see how that one comes out. For the vector A, its magnitude can be calculated as this using Pythagoras theorem: ax squared plus ay squared plus az squared. So the magnitude of A is expressed as, this is the vector A, so 3 squared plus plus 1 squared, or we say plus minus 1 squared plus 3 squared. That gives us a total of 19. This is 9 plus 9, 18. 18 plus 1, 19. So square root of 19. So the magnitude of A is 4.36 units. We do same for the vector B. Bx squared plus by squared plus bz squared. This gives us square root of bx is minus 1, so we say minus 1 squared. By is 2, say 2 squared, plus bz is minus 1 or squared. So this gives us 1 plus 4 is 5. 5 plus 1 is 6, so square root of 6, so that the magnitude of B gives us 2.45 units. Now we proceed to find the magnitude of A cross B, which is, this is A cross B, so the magnitude will be minus 5 squared plus 5 squared, which is square root of 50. So that A cross B will be equal to 7.07 units. So we can now find the angle between both vectors, saying sine theta is equal to A cross B all over magnitude of A times magnitude of B. This will give us 7.07 units all over 4.36 multiplied by 2.45 units. If we proceed, we say sine theta is equal to 7.07 all over 10.68. This gives us exactly 0.6620. So we find the sine inverse of that value to get the angle. So we say theta is equal to sine inverse of 0.6620, and that leaves us with 41.45 degrees. To one decimal place, we can say theta is approximately equal to 41.5 degrees. So this is the angle between the two vectors. You can see that we've been able to use the vector product to find the angle between two vectors. We can also use the scalar product for that. If we apply the scalar product to find the angle between both vectors, we are going to arrive at the same value. So my next lecture series will address some other more examples on vector multiplication. Then we also look at scalar multiplication in subsequent lecture series. Please remember to like, share my video, and of course, subscribe to my channel.